Hi, folks. Last time we learned how to do transformations of linear functions. And transformations of linear functions are actually a little bit tricky because straight lines have no features that you can track easily as you shift and transform the graph to different positions and stretch or shrink them. So we're also going to look at graphing absolute value functions and how to transform those. And absolute value functions have the general shape that you can see here in the bottom left-hand corner. They have a V shape to them, which actually makes it easier to do transformations with them because you can track where the vertex moves as you transform the function. What's a vertex? The vertex is this point where the graph changes direction. So the absolute value is decreasing, and then it changes direction, and it's increasing after the vertex. So an absolute value function is going to be a function that contains an absolute value expression in it. And the simplest absolute value function that there is f of x equals the absolute value of x. And that's what I have graphed here. F of x is the absolute value of x. Notice that the domain is all real numbers, but the range is not all real numbers. The range has to be positive values of y. Y is or equal to 0. So y is greater than or equal to 0. So let's look at the same kinds of transformations we did last class. Vertical translations, horizontal translations, vertical stretches, vertical shrinks, and also doing reflections. And horizontal reflections and stretches and shrinks as well. So let's start with vertical translations. Just like we saw with linear equations, sometimes the change that we make to the parent function affects the output values, and sometimes the change that we make affects the input values. So let's see how each of those changes affects the function. G of x equals the absolute value of x plus 3. So here I'm affecting the output value. That is to say, I do the original function, f of x equals the absolute value of x, and then I take that output value and I do an extra step to it, in this case, adding 3. When that happens, you get a change in the y direction. You get a vertical translation. So this is going to be a vertical shift, and we're going to go up 3 because we're impacting the output values. So let's, I've got a data table here for us to plug in values. If x is -2, the absolute value of x is 2, but then if I add 3 to that, that gives me a value of 5. If I start with -1, the absolute value is 1, but then I add 3 and I get 4. Starting with 0, I add 3. Starting with 1, adding 3, I get 4. 2 plus 3 equals 5. So notice that I'm just taking my original output value and I'm adding 3 to it. So if I go ahead and put this on the graph, I can see that my lowest point, my vertex, is now at the point 0, 3. And my graph just kind of increases on either side with a slope of 1. And so if I just carefully draw those lines in like this, this is the transformed function g of x compared to my original f of x. Notice that this has a vertex. The new location of my vertex is at 0, 3. My domain is all real numbers. And my range is Now the lowest possible value for my y is 3. So the y value needs to be greater than or equal to 3. So what happens when we do an equation that affects the input values? When our function here, this subtracting 2 occurs before I take the absolute value. So I'm changing the input values. Just like we did with linear functions in the last video, I've carefully chosen my x values here so that when I evaluate it, I will get the same output values that I did before. So for instance, when x is 0, I subtract 2 is negative 2, and then I take the absolute value and I get positive 2, just like I did for the original f of x function. So notice, originally I started with negative 2, now I'm starting with 0. Why did I add 2 to get that value? Because I'm going to subtract 2 in the function, so I have to do the opposite of what the function is going to cause me to do to the input. Similarly, with 1 here, 1 minus 2 is negative 1. Take the absolute value as positive 1. 0 minus 2 is negative 2. 2 minus 2 is 0. Take the absolute value and you get 0. 3 minus 2 is 1. The absolute value is 1. And 4 minus 2 is 2. Take the absolute value, and that is 2. So I've carefully chosen my x values here so that I will recreate the same y values that I had before. Now, because this is a negative 2, this is actually going to be a horizontal shift to the right. We're going to go right 2 units. Let me show you what I mean. When I'm at 0, I have a value of 2. When I'm at 1, I have a value of 1. When I'm at 2, I have a value of 0. 3, 1, 4, 2. So when I graph those points, and let me go a little further out here so I have, can try to draw a straight line. This, that last one wasn't so good. Try one more time. This is the graph of the absolute value function of m. This is my m of x function. This was a horizontal shift to the right. Why to the right? Remember, when you affect the input values, the change is kind of in the opposite direction to what you might be expecting given the sign of the number being added. How are we going to describe these transformations? Well, we can describe the vertex. The vertex is here at positive 2, 0. So 2, 0 is my vertex point. What's my domain? My domain for absolute value functions is pretty much always all real numbers. All real numbers. And then the range is going to be any value of y that is greater than or equal to 0. So that's how we do translations. Of course, if we wanted to have a shift to the left, we would need to have a positive number being added here. So like the absolute value of x plus 3 would give us a shift to the left of 3. And if we wanted to have a shift downward, we would have the absolute value of x minus some number, like 2. All right, let's look at another type of transformation. How about vertical stretching, shrinking, or reflecting? Remember, vertical is in the up and down direction and along the y-axis. So we expect these transformations to occur after the function is evaluated. We expect these transformations to affect the output values. The output values. So let's see if that is correct. Again, I've graphed the original function. F of x is the absolute value of x. And I'm going to evaluate q of x equals 2 times the absolute value of x. So I'm expecting this because it's in the y direction and I'm applying my transformation after doing the original function. That change is going to be what I expect it to be. If I'm multiplying it by 2, I'm expecting a stretch by a factor of 2. So this will give me a vertical stretch with a factor of times 2. So right now I have a point at negative 2, 2, right here. And I'm going to double that to get a new value of 4. So now I'll be up here at negative 2, 4. At negative 1, 1, I'm going to multiply that by 2, and my new position will be at 2. 0 times 2 is just 0, so I'm still going to have my vertex in the same place. 1 times 2 is going to give me a value of 2. So I'll have a point here. And 2 times 2 gives me a value of 4, so I'm going to have a point here. So if I just kind of continue that pattern up here a little bit to help me connect the dots. Here is my new function of q of x. How am I going to describe that absolute function? I can describe it with its vertex. The vertex is still at 0, 0. The domain is all real numbers in the x direction, all real numbers. And the range is going to be any value of y that's greater than or equal to 0. Let's look at p of x now. I don't want to do this in purple because we are still doing, here, I'll do it in orange. P of x is, notice that the transformation is being applied after the original absolute value function. So I'm still evaluating the absolute value function and then applying a multiplication factor to it. So this is still a vertical transformation. But this time, instead of being a stretch, it's going to be a shrink. It's going to be a shrink because the multiplication factor is less than 1. Not only is this going to be a vertical shrink, but because the multiplication factor has a negative sign on it, there's also going to be a flip across the x-axis. There's going to be a reflection across the x-axis. So my vertical shrink is a factor of 1/3, and there's a reflection across the x-axis. So what does that mean? If I start with a value of 2, the normal absolute value of x output would be 2, but I'm going to multiply that by negative 1/2, and I'm going to get a value of negative 1. If I have an input of negative 1, the absolute value is 1, but I'm going to multiply that by negative 1/2, and I'm going to get a value of negative 1/2. The absolute value of 0, I would normally get 0 as my output, but I multiply that by negative 1/2, and I still get 0. An input of 1 would normally give me an output of 1, but I would multiply it by negative 1/2, and I'll get negative 1/2. And an input of 2 would normally give me an output of 2, but I'm going to multiply that by negative 1/2 and get negative 1. So this graph, if I plot those 5 points, I have a point at negative 2, negative 1, negative 1.5, 0, 0, 1, -1/2, and 2, -1. So if I continue this pattern out a little bit further to help me draw my lines, my absolute value function looks like this. And that is the graph of the p of x function. Notice that it is a vertical shrink. The absolute value function has been kind of flattened out into a wider v, but it's also been reflected across the x-axis. When you reflect across the x-axis, notice that the x-intercept stays the same. And now we can work on describing this function. The vertex is still at 0, 0. Our domain is still all real numbers. But our range this time, instead of y always being greater than or equal to 0, y is going to be less than or equal to 0. All right. That takes care of vertical stretching and shrinking and reflecting. Let's look at horizontal stretching, shrinking, and reflecting. Remember, changes, transformations in the x direction are applied before you are applied to the input, okay? But before you evaluate the function, in this case, the absolute value. So these are all going to be changes to the inputs, because if you look, I'm multiplying my input by 2 before I do the absolute value function, or I'm multiplying x by -1/2 before I apply the absolute value function. To help you out, in this case, we're not starting with the original plain old f of x is the absolute value of x. This time I'm starting with a transform graph, absolute value of x plus 2, and the absolute value minus 3 is graphed here. Now I want to take that graph and I want to multiply the input by 2 before evaluating the function. So just to be clear, I've shown the modified equation here. Instead of doing x plus 2 in absolute value minus 3, I'm doing 2x plus 2 in the absolute value before I subtract the 3. So I've doubled the input. So if I plug -2 in here, -2 times 2 is -4, plus 2 is -2. Take that absolute value and it's 2, subtract 3 gives me -1. If it helps you to evaluate these on your calculator, remind yourself how to plug in those absolute values into your calculator, then that's a great strategy. I did, in this example, carefully choose those x values so that when I multiply them by 2, I go back to the original x values that I graphed to plot this function. So when I plug in -1.5, I get -2 as my output. When I plug in -1, I get -3 as my output. -0.5 gives me -2. Plugging in 0 gives me -1. Plugging in 1 gives me, I'm sorry, plugging in 0.5 gives me 0. Plugging in 1 gives me 1. So if I go ahead and graph this, -2, -1 gives me a point here. Then -1.5 and -2, -1 and -3, then -0.5 and 2, 0, -1, 0.5 and 0, 1 and 1. So this is the shape of my graph. And coming out here a bit further. And my graph looks like this. It is a horizontal shrink, of a factor of 1/2. Because the input values are affected, the change is the opposite to what you expect. This horizontal shrink by a factor of 1/2, notice that the the y-intercept is still the same. The y-intercept is unchanged. Okay. How would we describe this vertex this absolute value function? We can describe the vertex. The vertex is here at -1, -3. We can describe the domain. The domain is all real numbers. And we can describe the range as being values of y that are greater than or equal to -3. In this example, again, we're multiplying the input by a multiplication factor before doing the transformation. But this time it's negative and it's a fraction. So this is going to be some sort of horizontal stretch, and it's going to be a reflection across the y-axis. Because of that negative sign. So let's plot some points and find out what that means. So let's try some different input values and see what output values we get. Once again, I have carefully chosen my input values so that when I do this multiplication by -1/2, I get back to the original input value. In this case, for the first example, -4, so that my output will be -1. So let's see how this works. When I plug 8 into the function, I multiply 8 by -1/2, which brings me to -4, which was my original input value. -4 plus 2 is -2. Take the absolute value is 2, and then 2 minus 3 is -1. The next x input value I chose is 6, because when I multiply 6 times -1/2, it takes me to -3. -3 plus 2 is -1. Take the absolute value as 1. Subtract 3 is -2. So each of my output values for k of x correspond to my original f of x output values. So if I plot these on my coordinate plane, I have a point at 8, -1, 8, -1. I have a point at 6, -2. I didn't go far enough over. At 6, -2. I have a point at 4, -3. At 2, -2. And at 0, -1. Notice that this once again has the same y intercept. I have a point at -2, 0, and at -4, 1. So my graph has a wide V shape. A couple more points here. A wide V shape like this gives me my graph of k of x, as opposed to my graph of j of x. After graphing this horizontal stretch, we can see that we have a reflection across the y-axis. So instead of the vertex being in the negative x region, it's in the positive x region. My vertex is at positive 4, -3, -3. And the domain is all real numbers. And the range is any value of y that's greater than or equal to -3. How do we combine all of these transformations together? We're going to use something called vertex form. We're going to go back up here to the definition of vertex form. Vertex form is an absolute value function that can be written in the form g of x equals a times the absolute value of x minus h plus k, where a does not equal 0. It wouldn't be an absolute value function if a equaled 0. With vertex form is extremely convenient because the vertex can be written in the form hk. That is, whatever your subtracted value is inside the absolute value becomes your x value, and k becomes the y value of your vertex point. And then the absolute value v is symmetric at that x value for the vertex, where x equals h. So vertex form doesn't work for every single absolute value function. It only works when x does not have a coefficient in front of it inside the absolute value. So for the graphs we just plotted, vertex form does not work on those functions because there is a coefficient in front of x inside the absolute value function. A coefficient in front of x inside the absolute value function. Vertex form cannot be done on those functions, but it will work for this next example that we're going to do. So for this example down here, I have the graph of f of x equals the absolute value of x already plotted on this graph. And we want to graph g of x equals -2 times the absolute value of x minus 1 plus 3. Notice that this does have the form of the vertex form. A is a multiplier that's in front of the absolute value function. Inside the absolute value function, there's no coefficient in front of x. There is a subtraction problem. So -2 is my a value. 1 is h. Not -1, 1. Notice that negative sign is supposed to be there in the equation, and therefore my h value is just 1. And my k value is 3. So let's go through the steps of combining the transformations. First, step 0, check to make sure that your equation is in vertex form. And as we just demonstrated, it is. Our a value is -2, our h value is 1, and our k value is 3. Next, check for any horizontal shifts. We do have a horizontal shift. Horizontal shift is designated by this h value here. So that's going to cause a horizontal shift that is 1 to the right. So plotting this step on the graph, we want to shift 1 to the right. And so all of our other points just kind of get shifted 1 to the right. So the graph looks like this. And that's my plot of the step 1. So let me do step 2 in a different color here. Step 2, we use the absolute value of A to stretch or shrink the resulting graph. So I'm looking at the A value of -2, but I'm just going to think about 2 for right now. I'm going to ignore the negative. And that means that I'm going to have a stretch of a vertical stretch of 2. So now that my vertex is here, I want to stretch vertically. So when I go up 1 and to the right 1, if I'm stretching vertically, I'm by a factor of 2. Then when I go, instead of going over 1, up 1, I'm going to go over 1, up 2. Over 1, up 2, over 1, up 2. Continue the pattern. Basically, the slope is going to be 2 instead of 1. Or on this side, it's going to be -2 instead of -1. And this is going to be the graph of, this is going to be the step 2 that I've just graphed. Step 3, let me do this in a different color. If A is negative, then reflect the resulting graph across the x-axis. A is negative, so we are going to have a reflection across the x-axis. What does that look like? I'll need to scroll down a little bit. Instead of having my V pointing upwards, I'll have an upside down V, which extends with the same kind of slope that I had before. So I can just kind of take that line here and continue down in this direction and do the same thing on this side. Oh, that wasn't good. I thought I was finally getting the hang of doing these lines, but not quite. There we go. Looks like I need to connect 2 points to get it to snap into place. This is step 3 here with my reflection. And then with step 4, if there's any vertical translation, that happens last. So that K was my vertical translation, and I'm going to take care of that last. It's going to be a shift upwards of 3 units. So this is a vertical shift. Up 3. So instead of the vertex being here on the x-axis, I want to move up 1, 2, 3. But this is just a shift, so my slopes are still the same. I'm going to have a -2 slope down here in this direction. And I'll do the same thing here with my slope of +2 going in this direction. And this is my final graph after I've done my vertical shift. So overall, what did my transformation entail? I had a horizontal shift, 1 to the right. I had a vertical shift that was, I'm sorry, a vertical stretch. That was ×2. Then I reflected across the x-axis. And then I had a vertical shift up 3. positive 3. Just so that we can describe this graph completely, let's say the vertex, and so we did this step by step. You can also graph these using symmetry. So because this is in vertex form, we can use our h value, we can use our k value to find the point of the vertex. So the vertex point is at h comma k. Well, for this example, my h value is 1 and my k value is 3. So I know that my vertex is going to be at the point 1 comma 3. I can then use the fact that absolute value functions are symmetric to plot an additional point on the function. So pick any value for x other than 1. I could choose the value 0. So I go up to my original function, plug 0 in. 0 minus 1 is negative 1. Take the absolute value is 1 times negative 2 is negative 2. And then add 3, I get positive 1. So when x equals 0, y equals 1. And I know that absolute value slopes are consistent, so I can continue that pattern down this side. And because absolute value functions are symmetric, if my slope is positive 2 on the left half of the graph, then the slope is going to be negative 2 on the right side of the graph. So if you have the absolute value function in vertex form, you can use that vertex form to find the location of the vertex and then plot other points accordingly. I hope this helped.